Engineers tend to work with a variety of software packages and data types. For example, data acquisition systems, such as oscilloscopes, generally don't support MATLAB's native data type. So if I want to use MATLAB to analyze or plot the data, I need to convert the data to something that MATLAB can understand. MATLAB provides a variety of tools to perform this task. Low-level input-output commands can be tailored to read just about any kind of data in any combination. Some of the available data import commands are fread, fscanf, fgetl, and fgetS. Data export commands include fwrite and fprintf. The main categories of the commands are based on the type of data you're working with. fprintf, fscanf, fgetl, and fgetS all work with formatted text files. fread and fwrite work with binary files. When using these low-level commands, I also need to have MATLAB open the file before accessing it and close the file when I'm done with it. The relevant commands are fopen and fclose. First, I'll review the load command a little bit. The load command can be used to load files in MATLAB's native binary data format, typically files with a .mat extension. However, you can also use the load command to import ASCII data. To do this, I'll open the text file tempdata.txt using Notepad. This data is for calibration of a temperature measurement system. The measurement system outputs a voltage that changes with temperature. The data file gives a set of temperatures in the first column and the corresponding voltage from the measurement system in the second column. Notice that there are only numbers in this file, and the data is organized in a table in which all the rows have the same number of columns and all the columns have the same number of rows. I can load this data into MATLAB with load command. If the file's in the current working directory, I can just type a variable name, say A, followed by an assignment operator, the function, load, and the arguments to the load command in parentheses, the file name, tempdata.txt, in single quotes, and an ASCII specifier, -ASCII, at the command prompt. The data are loaded and placed in an array named A. This doesn't work as well if the data aren't in the form of a simple array. I'm going to modify the file to include some descriptive headings. The first line of the file is now going to be calibration data, and the second line will describe the data. Temp, a couple of spaces, and volts. Now I'll save the data and try to load it again. The load command doesn't know what to do now that the data aren't all numbers in the format of a table. One way to get around the problem is simply to copy and paste the data you want into the command window. In Notepad, just select the data you want and choose Edit and select Copy, or use Control-C on the keyboard to copy the data to the clipboard. Then go to MATLAB's command prompt, define a variable name, say B, an assignment operator, and an open square bracket to let MATLAB know that an array is being created. Then paste the data into the array. I'll use Control-V on the keyboard, and close the square brackets and press Enter. The Import Data icon on the Tools strip can also be used to load data into the workspace. Just click on the icon and choose the file you want to import the data from. An import window opens with the data represented on the left. Select the data you want, select how you want it to appear in the workspace. I'll choose to load the data as a matrix. Then click on the Import Selection button. If I look at the contents of the workspace now by typing whos at the command prompt, I see a matrix named tempdata, the same name as the file, and it contains the data I selected. The Import Data button works pretty much the same way for most file types. For example, the same temperature response data is in a Microsoft Excel file named temp.resp.xlsx. I can import this data by clicking on the Import Data icon, selecting the data I want, and again choosing how the data will be placed in the workspace. I'll select a matrix again. Then clicking on Import Selection. The matrix shows up in the workspace with the same name as the file again. Of course, I can also import Excel data by copying and pasting directly from Excel. I'll open the file from Windows Explorer, select the data I want, and copy it to the clipboard by pressing Ctrl-C. Now, just go to MATLAB's command window, define a variable named C, an assignment operator, and open square bracket again to indicate that we're defining an array, and paste the data into the array. I'll press Ctrl-V. Now just close the square brackets and press the Enter key. Before I go on to show other approaches, I'm going to delete all the variables I created in this demo by typing clear all. That's going to keep my workspace tidy for the next set of demos. Using the graphical user interfaces, or copying and pasting data into the command window, is fairly easy if you have a very limited amount of data you want to import into MATLAB. However, if you have a lot of data files with similar formats that you want to load, it's probably easier to use MATLAB's data import functions. The nice part about these is that the commands can be put into a script file, so that you can use one file to load and analyze the data. This keeps all your work together in one place. ASCII data is really common. I've already talked about using the load and save commands to import and export ASCII data. These are also useful for data that's in MATLAB's native binary format. Microsoft Excel data can be read into the workspace with the XLSRead command, and MATLAB data can be written to Microsoft Excel files with the XLSWrite command. Files in comma-separated variable, or .csv form, can be loaded into or exported from MATLAB with the CSVRead and CSVWrite commands. Sound files can be imported and exported with the audio read and audio write commands. Image files can be read and written with the imread and imwrite functions respectively. There are a lot of other supported file formats that are easy to find with MATLAB's help functions. Now let's do a couple of examples of using these commands. First, let's look at some comma-separated variable data. I'll open the rc_stepresponse.csv file using Excel. This data is a step response of an electrical circuit containing a resistor and a capacitor. The first column of the data is time. The second column is the voltage applied to the circuit, the input, and the third column is the voltage across the capacitor, the output voltage. The data I want to load into MATLAB starts in the third row and the first column. Now, arguments to the CSVRead command are the name of the file, the row and column at which you want to start collecting data. CSVRead, however, starts counting rows and columns from 0. So my first column is the column 0, and the third row will actually be row 2. The CSV command, therefore, is going to look like data equals the command CSVRead and the arguments. The file name in single quotes, so quote rc_stepresponse.csv, single quote, comma 2 to start reading at the second row, comma 0 to start reading at the first column. I'll end this command with a semicolon. There's a bunch of data here and I don't want to waste time watching it scroll by. I will, however, check the first few values by typing data of 1:5, comma, colon. So I'm going to look at the first 5 rows and all the columns. That looks about right. I'll plot the data by typing plot of data of colon, comma, 1. So all the rows in the first column, so that's time, comma, data of colon, comma, 2. So I'm plotting the second column of data versus time. Then I'll plot the third column of data versus time by saying data of colon, comma, 1, time, comma, data of colon, comma, 3. And that second line I'll put as a red dotted line, so quote R colon, end quote. Close the parentheses and press enter. The resulting figure looks pretty good. Next, I'm going to work with an audio file. They're kind of fun since you can actually hear the results of the mathematics. In this demo, I'll do a process called amplitude modulation applied to the song of a humpback whale. Amplitude modulation is the same process that's used to create AM radio signals. The amplitude of one signal is multiplied by the amplitude of a second signal. The signal I'm going to modulate the whale song with is a sinusoid. This will result in the song fading in and out with time. The humpback whale song is in my current working directory in the file named humpback.wav. I'll load the song by typing the output arguments in square brackets. So square bracket, humpback, that'll contain my samples, comma, fs, which contains my sampling frequency, close square brackets. Returning the sampling frequency is actually optional, but I will use it. Then, assignment operator, and the command name, audio read. The argument to that function is the name of the file in single quotes, so quote humpback.wav, end quote, and close the parentheses. First, I'll play the file by typing sound. Its arguments are the samples, which are in the variable humpback, and the sampling frequency fs, close parentheses. I'll also plot the data by typing plot of humpback. If I use only one argument in the plot function, it plots the values versus their indices in the array. Now, humans are visual creatures. The reason I'm doing this is that a graphical representation of the data can help us understand what's going on. So, this is what the samples look like. Now I'll amplitude modulate this signal. The signal I'm going to use to modulate the whale's song is a sinusoid. To do this, I'll first create an array containing the indices of the samples of the file. This array will just contain the numbers 1, 2, 3, and so on, up to the total number of samples in the file. I'll put these values in an array named samps by typing samps equals 1, colon, length of humpback. So these will just be the integers 1 up through the total number of samples in the humpback variable. Now this will be a row vector. My humpback song is in a column vector, so to make everything consistent, I'm going to transpose this to create a column vector by typing dot single quote, follow that with a semicolon because I don't want to see all these numbers scroll past, and press enter. Now I can create a sinusoid with the same number of samples as the whale song by typing mod, that's going to be my sinusoid, equals sine of 32 times pi times samps divided by the length of samps. Now what this will do, samps divided by the length of samps goes from 0 to 1 over the length of the song. Multiplying that by 32 pi means that I'll get a sinusoid with 16 periods over the length of the song. I can play back the sinusoid times the whale song by typing sound of humpback dot times mod, that's my sinusoid, comma, fs to send it the sampling frequency. You can hear the humpback song fade in and out as the sinusoid gets larger and smaller. Easy to verify this behavior by plotting the data. I'll type plot of samps, comma, mod. So that'll plot the sinusoid as a function of the samples. Then samps, comma, mod dot times humpback. So that'll plot the modulated signal as a function of the samples. And I'll change the line style, comma, r colon. There, it's pretty easy to see what the data looked like, and that makes sense relative to what we were hearing. The point of this demo is that I've imported some data, performed some operations on the data using MATLAB, and done some analysis by plotting the data. This is a pretty useful set of tools for an engineer. I can also export the data for use by other applications if I want. To create a file containing this data, named modwhale.wav, type audio write in its arguments. The file name in single quotes, quote, modwhale.wav, close quotes, the data that I want to put in that file, humpback.times mod, comma, the sampling frequency, fs. Now this file can be played back by other programs that use wave data. For example, opening the file with Windows Media Player results in the same sound we got from MATLAB. The input and output approaches I've covered in this video are really great and they're very easy to use, but they are a bit specialized. It's likely that they'll handle 90% of the data import and export needs you have, but there are cases where a more general approach can be helpful. The next video will present some additional commands which will allow you to customize your data import and export.